today to show you a little bit about the miniHIL and the continuous integration for embedded systems together with hardware in the loop. So first of all, who is Protoss? We're a software company that provides software tools, domain-specific languages, modeling tools, and so on for embedded systems. So we develop tools and tool chains. Then the second focus is we provide test tools. The miniHIL is such a test tool. And third point is we do a lot of software architecture, consulting, and doing for our customers. And altogether, we reduce the complexity for development of embedded systems. So that's our main focus here. So let's go into the meat. Why are we doing what we're doing today, or why am I talking about continuous integration in combination with hardware in the loop? Just imagine one picture. You're a developer of a cardiac stimulator for your heart, and you develop software for such a device. So what would this system test look like? Would you put it into a patient and let it run? That's a system test. Not very likely, because it endangers the person. There are other projects where you have maybe not such drastic effects in a system test, but where system tests are just extremely expensive. For example, if you change software in a car, you will not test this all kind of software by driving through the desert or something like that. So the main point here is the costs for fixing a bug or fixing problems is growing exponentially with the phase of the development. So what we are trying to achieve is to bring the system test and the integration test right at the developer's desk or at the continuous integration. So we try to test as early as possible. We need to learn and test earlier. That's the main focus here. Another point of view is if you have a look at the development process for embedded systems, many companies or many projects start with an evaluation board. They develop their drivers, they develop their hardware-related software components on top, like motor controllers, battery controllers, or CAN bus protocol. So any kind of hardware-related software part. And then on top, sitting the software components. Later in the project, everything is integrated to an application. And then most likely the ECU will be there at one point in time. And you try to put this on the ECU and run your application. So the question is, where do I test in this project, and what parts do I test? So the usual parts we're testing are the software components in the early stages by doing unit tests. That's very typical. Don't stop doing that. That's a very, very cheap and very effective way to test things, but usually only for pure software components. Later in the process, you have a hardware in the loop system test or a system test. System test in safety critical systems is a problem because you endanger people or you endanger lives. So you will most likely need a hardware in the loop test system. The problem is that the test system usually is developed very late, and it takes a long time for the turnaround. And the rest of the development process is not covered by tests usually. So that's where we're focusing here, on the integration test, on a simulated hardware in the loop system test for the early stages of the development. The acceptance tests usually are derived from system tests on system level, and you also can use a lot of integration tests or simulated system tests here to drive the acceptance tests. So the important thing here is many critical functions and many safety critical functions are really hard to test only with unit or with system tests. You need some kind of hardware in the loop test system. So why do we want hardware in the loop? First thing is we want to test things you cannot test with unit tests. For example, the integration with hardware, hard to test with unit tests, and the system level requirements. Another thing is you want to test things you must not or cannot test in the real system. You must not, because it's safety critical, you endanger lives if you test them in the real system, or the system doesn't even exist yet because you started with the software in parallel to the system development. And a third point here is the cost effectiveness. In many cases, it's really expensive to test in a real system instead of a simulated system or hardware in the loop system. And another important point here is you want to test the unhappy path. So not only the happy path, not only the regular use case, but also the errors, the problems, and so on. No? Failure injection and things like that. So that's why you need hardware in the loop usually. So why do we want continuous integration? So the second issue here. Let's have a look at the integration problem. So imagine you have an integrator. In many companies, that's a person. And the integrator, his job is to integrate all the software parts he gets from other developers. So you have the first developer, he commits 20 changes, another developer, and another developer, and suddenly there come a couple of more changes in. The integrator starts to get really worried. More commits, and in the end, the integrator has a real problem because usually the changes do not come in during the project, but at the end of the project, let's say minutes before the release or even days or weeks after the release. And so for the integrator, that's integration hell. That's exactly what happens in many projects. Everything is done. Every developer delivers his things maybe on time, but somebody has to integrate it. And by integrating this, you usually get a lot of errors. To solve this problem, you can use continuous integration. So how does this work? You have also developers, of course, they commit their changes to a source code management. So that's nothing new so far, but the changes in the source code management, they trigger the continuous integration server. In this case, also in my demo, a Jenkins server could be also a GitLab or whatever infrastructure you have. Doesn't really matter. Important is that it's automated. So the server usually automates the builds. So it builds the software. It runs automated tests. And it should also run automated releases. So please always deliver your software, even if you do not deliver it to the customer, but also delivery to the next department, for example, to the system test department or somebody else, or to a demo department or whatever, marketing department, whoever needs the software. Please automate the delivery as well, because if you automate the delivery, that means you can deliver anytime, at any point in time. And you will know that the delivery works because you do it all the time you change something. So the thing here is you need some principles to work with continuous integration. So every change is integrated and tested. That's important. So not nightly, not weekly, but every change. So within minutes, if possible. You need to commit early and often because you want to fail fast. If you make a change and you get an error message after 5 minutes, you still know what you changed. Next week, not so good. In 2 months, you have no idea what you changed. So fail fast, it's crucial for continuous integration, and continuous integration helps you to achieve that. So bugs can be detected and fixed very early in the process, sometimes within minutes. I'm going to show this in a demo afterwards. So what do I really want and need? We want to test every code change for every developer within minutes instead of weeks. That's really a very nice thing if you have that. We want full regression tests also for unrelated code. So if you change something in one module, code module, there might as well show up problems in another code module that's not that has not been changed. So it's very important to run full regression tests to discover side effects and things like that. And then you want full test automation to enforce tests. So you want to make sure that every change is always tested. And this can only be done by full test automation. So it's okay if you test this on your desktop, but it's better to test it on continuous integration in the end, because you make sure that it's always tested. And last but not least, you need automated hardware in the loop tests to test more than pure software units. It's good to make unit tests, but it's not sufficient to test your system. So why is it so hard to automate for embedded systems, so tests for embedded systems? One example is from a project we did. We needed to test the temperature shutdown for all border values for 300 relevant system states. So how is this done normally? Usually you have a climate chamber. In many projects, it's a huge device, a big climate chamber, 2 meters high and so on. And the problem with this climate chamber is it changes the temperature very slow because it's just a big chunk of metal. And what's usually done is you take the ECU, you take with the microcontroller, with the application into drivers, and with the temperature sensor. And then you start to bring the ECU in the right state, and then you rise the temperature or you lower the temperature to a point where you can test the shutdown of the system. The problem is because the system is so slow, it needs 2 to 3 hours. In this case, it's a real world case. It takes 2 or 3 hours to test one state. And for all the states, it needs 25 to 37 days. So this has never been done because it's just too long and it's not completely automated. So it's impossible to really test this complete. And even if you do, you have one test and not after every change. So what we did is we just focused on the microcontroller with the application software and the drivers. And we only test this smaller system. It's still a complete software, it's still the complete drivers, and it's still the right microcontroller. But we leave away all the electronic stuff on the outside, like temperature sensors and so on, and we simulate the sensors. And by doing that, we could reduce the integration test time to 10 seconds per state. By that, we could achieve, we could run all the tests for all needed 300 states within 50 minutes instead of 25 days. And of course, 50 minutes, that's something you can run easily on a continuous integration server after every commit. That's not a problem. Let's have a look at the typical response time for the test levels. So in the component test, like a unit test, usually you have a couple of minutes response time. Between 5 and 60 minutes is quite normal for an embedded system. Integration test usually is not done, at least not in an automated manner. Then you have the system test. Since it's so usually so huge or so costly, it's only you run only a system test every couple of weeks. That's a typical value. So if you get a response time for every error you find of a couple of weeks, it's really hard to develop. And the acceptance tests are basically derived from system tests, so that's why they have the same response time. So what we do here is we reduce or we introduce the integration test with a miniHIL. So we focus only on the microcontroller plus drivers plus the complete software. and we can reduce the testing time to minutes instead of weeks. And we still get a lot of system relevant tests here. And you can bring the test setup to the developer's desktop or to the continuous integration server. So the idea is here to have a very fast turnaround by test automation every 5 to 60 minutes instead of weeks. So we close the testing gap here. Let's have a closer look at the hardware. We're providing, our motto is keep it as simple as possible. Maybe you know it's a saying from Einstein. So we developed a hardware platform to only focus on the test of the microcontroller plus software. And in this case, it's a drilling machine of a well-known company here. That's a Cortex M4. So that's the system under test here, exactly as it's installed inside the drilling machine. Then on the other side, we have a microcontroller that runs the environment simulation and the test cases. So you need both things. You need environment simulation with motor plant simulation, with a battery plant simulation, with all the protocols and things like that. And you also want automated test cases to actually prove that things work or don't work. You can connect both systems with the usual I/O, digital, analog I/O, SPI, I2C, and so on. So everything normal microcontroller provides. And then you can run the tests here. That's a typical setup on the desktop for one project. So you have your software on your laptop for development, for creating test cases and so on. And you have the miniHIL board sitting right next to your laptop. And either you click to start the test or you have a continuous integration set up on your laptop. That's easily possible. And you run the continuous integration server on your laptop. That's a good way to start. So you don't need specialized hardware for that. You can just run it on a laptop. That's a setup for one project or for one developer. That's a very nice thing to do. If you have more projects or more developers, then it's a nice thing to have a continuous integration server, a dedicated server. And for example, in this case, we have installed 8 miniHIL boards in a rack. So those are 8 different projects that are run by the continuous integration server. Whenever somebody commits something in any of those projects, accordingly the test is executed. So the idea is you change code. Every code change is automatically built, tested, and delivered. And you get a fast feedback, very fast feedback, often within minutes. If you have long-running tests, then divide them into stages. Commit stage, 5 minutes, 10 minutes maximum. You have fast response. And then in the next stage, you run the longer running tests. Every hour or every couple of hours, you trigger the longer running tests. And by that, you get still a fast response and you get all the depth you need in the end. And in the end, of course, you need to deliver. You can also automate this very good with a continuous integration server. So I brought you a little demo test system to demonstrate what we can do right here on my laptop. The idea is here we have a system under test. That's the STM32 microcontroller in this case. Could also be an Oryx for automotive system or TLE or an XMC or whatever it is. So it doesn't really matter. So all kinds of 16 or 32-bit microcontrollers you can test very good with the system. On this system, we have a BLDC motor controller running that has outputs 3 PWMs, block commuted PWMs. And on the test system, we have a plant simulation of this BLDC motor which generates 3 Hall signals as digital outputs. They are measured in the microcontroller here in the system under test, and that's the control loop then. Another interface here in this test system or in this demo system is a UART. Yeah, usually you control somehow the motor control system via UART, via CAN, LIN, or whatever protocol you run. In this case, we used UART because it's easy to demonstrate, and we wanted to keep the demonstration here pretty simple. No? But it's a real-world simulation, so it's yeah, it's reality. Let's have a look at the same setup or at the test case from the electrical perspective. That's a Salea log from a logic analyzer, not from our company, but yeah, it's a product you can buy, and we just connected it to our running test system. And here you can see the PWMs, for example, and the Hall signals that are generated by the simulator. Here the speed control. If we change the speed, the PWM goes from 50% to 90%, and accordingly the Hall signals, they get closer, they get faster, and that's how we simulate and how we test the system on an electrical level. So let's go into the demonstration. I'm going to switch to first of all to my hardware setup. Here we have the hardware setup. That's the microcontroller, the Cortex M4. Then we have the 3 PWMs, three digital inputs, and I guess that's the serial interface. So the UART interface, and yeah, that's basically the wiring you've seen also in the diagrams before. And on this processor here, we have the environment simulation, the motor, the plant simulation for the motor controller, and also the test cases. So it's all running on this microcontroller here, because then we have a hard real-time system, and we can test down to microseconds. So for example, for a motor control, you need 20-30 kilohertz simulation, and that's easily done with this setup. It's a very hard deterministic setup, and we can even go down into the range of 10 microseconds. With a FPGA, we can go down into the megahertz range. So that's the hardware system, and I'm going to show you how the software is developed. We have a model-based approach. I'm just diving a little bit into the modeling here because that's not the main focus, but we built based on this modeling language here. It's called real-time object-oriented modeling. We built the environment simulation by first, and the test cases by first providing the I/O infrastructure, so the Hall generator, the duty capture for the PWMs, UART adapter, digital analog outputs, and so on. So that's that's mostly provided by our framework. You can also add your own drivers or whatever it is. And then we have a motor simulator that's in this case realized as a state machine. And it's generated directly from this model, the C code. And then we have the test cases. They are described as test language, which also provides graphical views for the things you can describe. So if I change something here in a test case, you can see what happens in the graphical specification. So that's always directly derived from the model. And of course, for a single step, that's very simple, doesn't give you much benefit. But if you go, for example, to a whole test suite, then you can see the whole specification for the whole test suite, and that's really nice, because on that level you can discuss really good what's missing and how you want to design your test cases. Yeah, so let's have a look at the continuous integration. So that's the hardware in the loop setup. I can start it manually. I'm going to demonstrate you that also. So we have the, oh, just a second here, the camera. So here I have the hardware loop system. I connect it. Now it's, you can see it blinking here. I can turn on the LED on the hardware board. And but that's not the point. The point is I have those automatable test cases or automated test cases. I can trigger them manually on my desktop now. So for example, to show you what happens if I mess something up here, I run the tests and I pull a plug and let's see what happens. We have a lot of errors here. I repair the system and the errors are gone again. So that's how the system is run on desktop. If you develop test cases, it's really nice to execute them directly on your desktop. But the important issue is here, we want to automate the tests. So let's have a look at the continuous integration server. I started a Jenkins continuous integration server on my laptop here. Here's the web interface that's on localhost, and it's monitoring every change in the application software. So now I'm going to go into application software. That's, by the way, I have in the same IDE, I have the test project and the application project just for demo purposes. So the device under test STM32, that's the demo, that's a system under test, and the rest is the test system. And now I'm going to change a line of code just to show you what happens. So I'm changing a line of code here. I say UART. Let's take this UART and put it to 0. So this should change something. And now I'm going to commit this. That's a regular Git on Git server on localhost here. I add it to index and I'm going to commit it. So let's name this commit bug. So now I committed it to the server, to the continuous to the Git repository. And let's have a look at the continuous integration server here. So the continuous integration server now checks, in this case, every minute whether there have been changes in the Git repository, and it executes directly the build of the device under test. The test system is also generated and built automatically. Then both images are flashed on the board. So the device under test is flashed exactly as it's, so exactly the application as it's delivered. So without changes, it's a black box test. And then our system under test is also flashed. Our test system is also flashed. Now you see it has detected a change. And now let's have a look at what happens. It checks out the latest changes, and then now it assembles the project. It builds the project. So it builds the device under test and the test system. Then the system is flashed. Let's have a look at what happens on the board. Now the lamps here should change when it's flashing. So now you see it stopped blinking. And now, yeah, it's flashed. So let's go back to the continuous integration server, and the continuous integration server now executes the test cases when it's flashed. Couple of seconds, you can see the log with the target, how it's built, and so on. And it's done. So almost 24 seconds, yeah, something like that. So the average time here in this case, because we built incrementally on a real continuous integration server, I would check this always out completely. clean it completely before every test run and so on. So, and now we can see the result. Everything is green because it could build and it could execute the test cases, but the test cases themselves, they are yellow. And why is that? Because here you can see 2 test cases have not been right. And here you see 2 of the integration tests have been wrong. So that's an answer within a minute or so. In real world projects, it's maybe a couple of minutes or 15 minutes or something like that, depending on how much you test, how much you automate, and how your stages are. So now, when I know that 2 test cases have failed, I need some more detailed information about what happened there. So let's have a look at the log from the target. Now we already know the sequence diagrams from the specification. And now we have the sequence diagram directly derived from the target log. So we also change this into, convert this into a diagram. I click on the expect here, and it opens my IDE. And here I'm exactly at the point where my system failed. So it's the step check speed that failed. And that's exactly what I saw in the continuous integration server here. That was exactly the thing that failed. So that's the low level view. You need to so this one here is the low level view. You need to really know the point where your system actually failed. And then we also provide high level views, like for example the feature traceability. In this case, you see the 2 test cases that failed, and also which requirements are working or are tested by this test. Here, for example, the robustness test have much more test cases, and so on. Good. So last but not least, I said, please do always deliver the software. This means always build the software as if you would deliver it to somebody, to your customer. Build the documentation, execute all the test cases, of course, and create the bundle as if you would deliver it to the customer. And the bundle usually also needs the documentation. In this case, the test documentation, which is also generated directly from the models here. For example, the state transition test, that's a combinatorial tests. If you have a safety critical systems, that's very, very handy. But also for other systems, it just provides a very deep testing here. So that's the test documentation, and so on. So that was the live demonstration of the running continuous integration server on my laptop, together with the hardware in the loop test system. And let's wrap this up. At the end, I would like to give you a couple of best practices for continuous integration for embedded systems. First of all, unit tests are very simple to automate with continuous integration. Please start here. Create a couple of unit tests if it makes sense for you, and run them on a continuous integration server. It's really helpful, and it's really easy to do, and simple and cheap. So you should definitely do that. But if you need hardware in the loop tests for integration and system tests, they are hard to automate. So keep it simple. Keep it as simple as possible, because if it gets too complex, too big, too expensive, you cannot automate this really good. And sometimes you cannot automate, you could automate, but you cannot automate because the equipment is so expensive that everybody wants the equipment. And so it's never on standby for the continuous integration and waiting for a commit, because it's always used for something else. First, you have to change the system, adapt it to your project, and then you can run the tests. That's not automation, at least not as I understand it. Something very important in general is, if you have test methods, you need to run them, be able to run them on command line. In this case, everything I've shown you also runs on command line because you need the command line to integrate it with all kinds of continuous integration systems. That's the most simple way to integrate everything with continuous integration. If it runs on command line, you can use virtually any continuous integration server. And also automate metrics and documentation. Documentation I've shown you. Metrics, it's important to trigger decisions or to trigger actions. For example, if you have metrics for certain design guidelines or for complexity or something like that, that's no proof of quality, but it helps you a lot to detect holes in your test strategy or hotspots for problems or things like that. It's no proof of quality, but it helps a lot to detect problems in your system. And then automate delivery. I guess I already made that point. And in the end, aim for fail fast within minutes instead of months. So fail fast is the most important thing if you test stuff in embedded systems and other systems as well. It's hard to achieve with embedded systems. And so try to fail within minutes instead of months. Good. So that was the technical presentation from my side. If you have any further questions or projects or whatever, we're open for discussion. We're open to help you. Michael Weiss from Hitex is responsible for the miniHIL projects on Hitex side. They provide the services around the miniHIL and so on. And yeah, you can also ask me if you have technical questions or ideas or whatever you want to discuss. Please don't hesitate and contact us. So that's it from my side. Thanks a lot.